Hello, and welcome to another episode of the Lateral Think podcast. Today, I'm very fortunate to be joined by Graham Scarr. Graham, thank you for being with us today.
Thank you. Glad to be here.
So, Graham, to start the conversation and to give some context to what we're going to talk about, can you give an introduction to who you are and what you do?
Yes, I'm a retired osteopath, charter biologist. I've got a pension. The government pays me to drink tea all day, which is far from the truth because I actually busier than I've ever been in my life. Um, I should really start at the beginning because I was interested when Jack gave me an idea of what we might be talking about. He suggested some of my history, how I got to where I am now, which is really good because so many people ask if I want to talk about Biotensegrity or whatever. They just want the goods of that subject. But actually, it's got a history that goes back to when I was 10 years old onwards. And I think it's relevant to where we're going to get to later in the talk.
Yeah, please do.
So when I was 10 years old, I wanted to be a naturalist. I had no idea what one of those was really, except it was about nature, animals and plants. And I was fascinated by patterns and shapes, natural patterns and shapes. So I would cut pictures out of magazines and put them in a scrapbook and save them. And I did that for perhaps 5, 10 years. Then when I left school, I got a job in a bacteriological research lab, researching the bacteria of cows' stomachs, which was really interesting because it involved some really cutting edge research at the time, developing ways to culture these organisms in ways that hadn't been done before, and fascinating. But at 22 years of age, I wanted to see the world, so I went to university and did a degree on microbiology,
Mm.
and that was all really good stuff. Then I had a break for a few years doing bits and pieces, other jobs, not at all related to science, until I decided I think I want to be an osteopath because my grandfather was an osteopath. And so within a few weeks, I'd sold my house, gone off, applied, gone to the European School of Osteopathy in Mason in Kent.
Hmm.
And I did 4 years there to get a diploma in osteopathy. I then practiced and off I went. That was my career for the rest of my life, or so I thought. And of course, I was taught the standard scientific stuff, how the body works, mechanics, biology, of course, all the clinical applications, the theory and practicality. And I was treating patients for, 10 or more years, 12, 13 years. And, but I always felt there was something missing because standard biomechanics is all about machine model. I learned about machines and levers, and this is how the body works because that's what the textbooks tell me. And so that's what I thought. But I found in practice that things weren't quite like that. So I would, for example, be working on somebody's left shoulder. And while I was working on it, they would say they could feel what I was doing in the right knee or somewhere else. And I thought that's odd because the nervous system doesn't connect those two together in a way that made sense to me. And I worked as a cranial osteopath, so it's all very gentle techniques, or craniosacral therapy, it's otherwise known. And so it's very gentle. You can feel all sorts of things happening. But this puzzled me, and I didn't know where to find answers. So in one day I got a flyer through the post. Well, no, it was a magazine, Osteopath magazine, with an article describing a different way of understanding the body called Tensegrity. I thought that's interesting. I don't know what this is about. On the picture, on the front cover of the article, was a picture of a six-strut tensegrity, which otherwise known as a tensegrity icosahedron or T-icosa or expanded octahedron, for reasons which I'll explain the different names later. And I read this, and it was that picture, because it had a pattern, a symmetry to it that really appealed. And I read the article as well.
Mhm.
And reading the article, I thought I must find out more about this. But this is over 20 years ago, and there wasn't much written about tensegrity in biology then. And so I looked through my catalogue of cuttings and found all sorts of articles from several years before that I'd saved as something of interest but never actually read. And one was Donald Ingber's article, Tensegrity. I can't remember the article, but the architecture of life. Yes, that was it. Tensegrity, the architecture of life. And wow, I read that through, and that I also found things by Stephen Levin in the US, who'd written several articles, picked them up, read them, and I was really, really taken by this. And because of my practical training with making model aeroplanes, also in the microbiology lab, I wanted to make one of these models.
Mm.
So I got all the bits together and had to figure it out just from this plain picture, put it together, and there was something clearly wrong about it. And after a while, I realized that the drawing had been incorrectly done. There was a couple of mistakes in it, where the strings went and everything. So I changed that quickly. Totally had this beautiful, I didn't bring one with me, but I can get one in a moment, beautiful six-strut tensegrity structure. It was really light in weight, where the struts are all like suspended within the tension network of cables. And when we compress the two sides together, the whole thing collapses down. But it doesn't collapse. It shrinks down to a smaller space and expands out again like this, which is really, whoa, I must need more about this. So I contacted Stephen Levin, and we had a few chats, and we met up a few months later, and that was the beginning for me. Didn't know what to do with it. It was just fascinating, interesting. It got me into seeing, well, where does tensegrity occur in the body? Well, I can't see these tensegrity icosahedron models anywhere. So I tried to find out by thinking of, well, the skull. That's what I work on a lot, the cranial vault. I wonder if that's a tensegrity, because it's got a sort of roundish shape. And I got the books out, and yes, I'd done a lot of anatomy of the skull previously, but I used to look at more detail, the actual sutures between all the bones. And for those who don't know, or may do, but the cranial vault are the bones that cover the front, top, and sides of the skull of the brain. And there's 8 bones with that. There's about 22 bones in the skull altogether, most of which have a bit of flexibility between them. The skull is not a solid box, or shouldn't be. So if there's a bit of give between those bones, then maybe this tensegrity model has got something to do with it. So I discovered more about the bones, how they're produced, how they grow, and that the standard view is that the growing brain pushes the bones outwards, but no one knows how it does this. And it's also found in later work that the growing brain can't push the bones outwards. So what makes the bones grow? What makes the brain grow? And how do they keep it sync with each other so the growing brain isn't squashed by the skull bones? And reading more about this, I reasoned that the skull as a tensegrity structure was a feasible proposition, and wrote a paper on it, which was published in the International Journal of Osteopathic Medicine. And I thought, oh, that's very nice. With very little changes to it. Most papers I write, the reviewers come back and say, you got to do this, that, and everything else. But this one passed through. It has not flaws, but things I would change if I rewrote it now. But anyway,
Mm.
so that started me off in my first model. And then I carried on making more models, looking more at anatomy books in much more detail, learning a lot all the time because I was fascinated. I mean, when I was a student osteopath, of course, we had theory on anatomy. So anatomy that really appealed to me. The practical things, of course, I had to learn that stuff, practice it, had to be proficient for when I graduated, which
Mm.
I was because I graduated. But its anatomy always appealed to me, physiology, and that took me up to where I am now, and lots of bits in between. But how's that for a start, Jack?
It's a very good start indeed. And there's a couple of things that you mentioned, Graham, that I think are very important to explore further. One of the first things you mentioned was early on, you're learning about the mechanics of the body. And as you briefly mentioned, a lot of the models for how we look at human movement is simple, simple physical models of looking at lever arms and looking at creating torque. But as you mentioned, there's a lot of limitations to that. I'd be interested to hear your thoughts on that further. Of what are some of the limitations to these simplistic models of mechanics, and I think more importantly too, a question I've often asked myself is the difference between mechanics versus biomechanics, because I feel like that's something that is often not explained well, and as a result, we tend to just use simple mechanical laws and assume that that applies to biological systems like humans.
Yes, yes, yes. I mean, biomechanics, as you find in the textbooks, started 450 years ago. Um, Descartes, Borelli, Newton all thought the body operated like a machine. Giovanni Borelli, he compared the workings of man-made machines around him
Mm.
with the human body, or vice versa, compare the human body with man-made machines of that time, and wrote a book about it in 1680. And it made sense. I mean, it was revolutionary at the time because no one really knew how the body works, but this now provided an explanation with levers, pulleys, great stuff, really great. And that dominated biomechanical thinking until, well, it's still dominant now. Current biomechanical
Absolutely.
books still think the body works like a machine. They still
Yes.
publish textbooks, the body is a machine, and the lever is central to that. But at least over 100 years ago, there were people questioning the body can't be a machine. It's much more complicated than a machine. A machine is sort of fixed parts that interact with each other and can interact with each other in many complex ways. But this is the standard stuff. And the great thing is it can be analyzed mathematically. Descartes' algebraic approach to geometry, structural analysis, equations, formula. Great. You can do all sorts of things in it. You can do calculations. You can put them in a computer and have a model of an arm or a leg or any bit of the body. It'll chuck out a load of numbers and give you a great model that can appear to act just like the real thing. But appearances can be deceptive because all models are wrong, just that some are useful.
Mm.
And biomechanics established itself. This is the way to go on. But there's a problem with levers. Well, living systems operate with this. Let me go back. Pardon me. Let me go back a moment to standard machines tend to operate linearly, a
Mm.
linear stress strain curve. So if you stretch something, it will strain will be sort of proportional to it. Hooke's law of elasticity. Stretch something, the amount of force you put is equal to or proportional to the amount of stretch given in that thing.
Mm.
But living systems operate non-linearly. It means the slope of the stress-strain curve is not a straight line, it has a curve to it, which complicates structural analysis. It makes it really complicated. So rather than thinking of a straight line, they can't do because it starts in a curve like this. They think the last part of the curve, where it goes up like that, they think that bit is a straight line. And the
Mm.
first bit is sort of not really important. So they
Mm.
look at the high stress strain part of the curve and think that's how the body works. Why would living systems operate at a high stress strain rate when they can operate at a low stress strain, where they can be more efficient, more responsive, and much better survive much longer because they're not put on these high stresses? So this is sort of pushed aside as an inconvenience. And it's well recognized. Any biomechanic, mechanical engineer, biomechanic would recognize that the approximations in what they do. They recognize that all their models are approximations. They make assumptions. They know that we can't get right down to the lowest level because computers just can't get down to that amount of detail. But they push it aside. Oh, yes, it's an inconvenience, but we can do all this, all these main great things we can do. We can put it on a computer screen. We can even make models. Oh, it's fantastic stuff. But human body, the whole of biology works quite differently.
Mm.
And because every plant and animal has a different origins, which goes back through evolution to 2-3 billion years ago, they all came from similar origins back then and evolved into the huge diversity of life, all which function more or less the same. So I digressed a bit from the lever model. I want to put another bit of the lever model in, which is
Please do.
that yes, when we assume that the body works through a system of levers and a musculoskeletal system, so the muscles move the bones are the skeleton of the body, and the muscles simply move them around. And that's great. You've got two systems. You've got a hard system of bones, a soft system of muscles that move them around. Oh, great. We can make these models now. We can go into all the details of the muscles, the fibers, and the blood supply, and the actin and myosin molecules. Oh, this is great stuff. But living systems can change. They're changing all the time. Everything about them is changing. Whereas machines are relatively fixed. And I'm just thinking how to get this through to where I want to be. It's assumed that the muscles provide a stability for the bones, that the nervous system controls
Mm.
the muscles.
Mm.
That's good. That's fine. Yeah, great. I'll go with that. The trouble is that muscles and bones and a lever system can't necessarily cope with sudden change in the system. Sudden when we're eating, when we're talking, the jaw's moving fast, the tongue, the vocal cords, it's all happening really fast. If we're biting a nut, suddenly we hit the nut, instead of grinding down, we instantly move away to the side. And sometimes we grind into the nut and break off the end of the tooth because the nervous system can't control the muscle system fast enough to overcome those problems. Now, that's an extreme example. But in everyday activities, we do all the sorts of things we do. But if we get an unforeseen impact, it can cause problems before the muscle system has had time to react because of what are called force transients. So if I hit my hand, we tend to think it's a sudden impact. Oh, that's terrible. But actually, when I hit my hand, there's all sorts of things going on in there. The force has to transfer into the hand. It's going to be so fast, the tissues, if I did it really hard, wouldn't be able to compensate for that. But these force transients are very fast. I can show you I wasn't prepared for showing pictures, but there's it's probably
Yes.
upside down, I don't know, but
No, that's right.
there's the
I can.
force, and
Yep.
these are the acceleration and the other things that are happening after it. I mean, the period between there and there might be milliseconds or a second or two.
Mm,
The point is that it's now shown that a lever system working through a muscle system controlled by the nervous system is capable of overcoming all the problems that a living system can be beset with.
mm,
So that's what really and came out in the paper, came up published in January, moving beyond Vesalius, why anatomy needs a mapping update. And first of all, had to demolish this idea that the body operates like a lever system, and that the
mm,
musculoskeletal system, although it's in all the textbooks, in our practices, we talk about the musculoskeletal system, but it proposed an alternative based on 17th century science, which was prominent, which was a concept that rivaled the musculoskeletal system, and actually which put the fascial system at the
mm.
prime motor of movement. So that paper really got me into that.
And this is where I think an important
So
part of. I wasn't going to
I've
say
gone a
that.
long way
That's
from
a.
your question.
Oh yeah, I was just going to say. I think this actually takes us to another important point, and that is the discussion about fascia. Because as you mentioned in your recent publication, moving beyond Vesalius. So much of what we learn about anatomy is looking at the musculoskeletal system, where you have the muscular component and the skeletal component, and these are separate tissue structures. And part of this is because the fact that fascia is often removed through the dissection of a human body as well. So we have this illusion, so to speak, that the fascial system is something that doesn't actually exist, or at least we're told that it has very little relevance to the mechanics or the connections of the human body. Can you
Mm.
actually talk a little bit more about that and specifically um, some of the
Yeah, yeah.
limitations of how we view anatomy based on the limitations of removing the fascial system and the implications that has for some of the models that you were talking about?
Yes, and of course the biomechanics recognise bits of the fascia. They recognise the tendons, the
Mm,
things they call ligaments, and I'll talk about that, which are not necessarily what we think they are. Um, Tendons, ligaments, aponeuroses, septa. They recognise these things, but they're just ancillary bits of what we now call fascia. Yeah, they're useful, but this rest of this flimsy stuff that surrounds blood vessels and muscles. I mean, yeah, it's okay, but do you want to waste your time on this stuff? Is their general attitude. Um, but fascia's enormously important. And as uh, I guess many of you watching are manual therapists of one sort or other will recognize the importance of the fascial system. And I wanted to know more about it. And so 10, 12 years ago, I set off to do a human dissection course, which was focused on the fascia. The intention was to look at the fascia. Yes, I hadn't seen the heart and muscles and bones it wasn't in cadavers before, only in textbooks, but to see the real thing where the fascia was kept intact, and it taught me a lot, and which then brought me to where I am now. Um, so the fascia from the paper, I reasoned a few years ago that the fascia is organised into compartments. Now, it wasn't just my idea. I'd read this word compartments all over the place, just sporadically. Someone would talk about the muscle compartments, the compartments here, compartments there, but there was no unified thing that put it together. I reasoned, I got to understand more of this, write all these different compartment examples up. And I happened to be talking to somebody, actually from Australia,
Mm.
who told me about an article that was published in 1944 that highlighted this very thing about the fascial system as a system of compartments. In the 17th century, Robert Hooke, the chap who described the laws of elasticity, where you put a force to stretch, like stretching a rubber band, you put 1 kilogram here, stretches this much, 2 kilograms, 4 kilograms, so it's proportional between the force and the stretch. And he declared that, recognized a cell as a small compartment in a larger structure. And he took examples with his new microscope, looking at cork, at a cross-section of cork, and he noticed all these little holes in it, which he called cells. And then along came Marcello Malpighi, who was a good friend of Robert Hooke, and he thought, well, maybe these things don't just occur in plants, like Hooke had noticed, but perhaps also occur in animals. He got his microscope out, started looking, and hey presto, there was a little compartments with stuff inside them. Didn't know what the stuff inside them was, but you could see they were arranged in the same way, these compartments. And he called them cellular tissue. Now, the term cellular tissue then had a quite different meaning than it does today, because then cellular tissue meant these fascial compartments or connective tissue compartments that contained, well, didn't quite know what they contained. They knew it was this sort of gooey stuff because they could only look by dead animals or cadavers, and often these are starting to rot by that time. But as Lamarck, who's had bad press for all sorts of things, he said that compartments are I paraphrase, the mainstay of the human body, and without this structure, no living body could exist.
Mm.
So he was really enthusiastic about compartments, and he wrote this, I think, in the late 18th century. And this became the standard model for understanding the human body. The musculoskeletal system was there, but it was sort of not as well understood. Then, of course, along came Schwann with his nucleated cell theory. He noticed these are very much smaller nucleated cells, muscle cells, epithelial cells, nerve cells, all sorts of different types of cells. In the late 18th, early 19th century. And of course, that took off like a rocket. And the muscular system and skeletal system, they could now see the cells inside them. And the fascial compartments thing just vanished altogether. It was completely overtaken and forgotten about, more or less, until the last 20 years when interest in the fascia started to resume. But even then, no one was talking about fascial compartments, really. So we know about compartment syndrome. Yes, the pathology was recognised, where some restriction in blood flow in the muscles causes increase in pressure in the fascial compartment, which then causes pain and paralysis, often requires surgery to resolve. So the fascial compartments were recognised, but everything else just fell away. So the fascia is important for everything we do. The trouble is we can't see it when we're working. We know it's there, and we can get a different idea of what's going in, which makes the musculoskeletal system a bit obsolete, because we have muscle compartments, we have bony compartments, and Stephen Levin, the founder of, or the originator of Biotensegrity, he recognized that bone is actually part of the fascia, same as muscles are part of the fascia, because they've got the same origins. They just appear different shapes, different structures, but actually they have their origins in the same mesenchymal tissue. And a few people picked up on this. Some people thought it was crazy. So this article, Moving Beyond Vesalius, it put it all together where the fascial system is now the primary motor of movement. The muscles are tensioning the fascia. That's their function. If they tension the fascia in a particular way, that is what leads to what we call movement, how the body
Mm.
moves around and stuff like that. But now we've got a different concept of what the fascia is. The musculoskeletal system is obsolete, and I reckon forget about it altogether, except, of course, we have to talk to other people and talk to our clients. So I know it won't disappear just like that, but
Mhm.
I won't be using it in the traditional context.
No, and what you highlight there
So
then
the
is,
fascia is important.
I was just going to say, Graham. So what you really highlight there is, it is ultimately a tissue system that unifies and connects the body in the most literal sense possible. Because in reality, when you look at it, the anatomical relationship of fascia to muscle and bone, you see that this is not just some arbitrary relationship, but it actually has a very intimate connection. And you see this in the sense of many muscles actually originate from the fascial system, or there are expansions between the muscle and the fascial system as well.
Mm,
And then it actually provides shape for how muscles fit in the body. And I have heard of that concept before of the muscular
yes.
system is simply a system that helps regulate tension within the fascial system to allow force, well, to allow movement to occur. And obviously, how movement occurs is through the transmission of forces from the muscular system to the fascial system, and of course, of which there are some strong connections to the fascial system and bone through things like tendons that allow movement to occur.
Mm.
Mhm. Can you? I was
Yes,
going to
very
say,
right. And I must
no,
add to that, as nicely.
go on. No, please add to that. Yes.
Oh, all right. I beg your pardon. Yes, it's delay. So I wanted to add to that. I mean, what else do muscles do except tension the fascia? They probably do other things as well. I can't think offhand. But I want to point out ligaments.
Mm.
We think, no, the textbooks think, I won't say we, the textbooks say the muscles transfer their force through tendons to the bone. That's okay. They don't always do that.
Mm.
It's been shown that muscles transfer their tension through the epimysium, that's a surrounding piece of fascia on the outside of the muscles. They
Yes.
transfer that tension to other muscles, even antagonistic muscles.
Mm.
So when a muscle is active, contracts, some of that tension goes to the muscles, is antagonistic muscles, which is part of, goes to even antagonistic muscles. So it's much more complicated than single muscle doing a single movement, because
Mm.
all muscles operating all the time, all muscles are under tension all the time.
Mm.
That is why the stress strain curve doesn't start from zero stress,
Mm.
because of the intrinsic tension contained within the tissues, within living tissues, all the time. And the thing about tensegrity, the same occurs in a tensegrity, because it's automatically pre-stressed. So back to the ligaments, as was shown 20 odd years ago and more in the elbow joint, that rather than the elbow muscles transferring the force through the common extensor tendon to the bone, like all the textbooks would say, Van der Waal showed that the muscles were transferring their tensional force to the ligaments to the bone, and that he found that the collagen alignment within ligaments in the elbow, at least, was not between bone and bone, but between muscle fibers, the fascia, and
Mhm.
bone. And that what we call ligaments in the elbow and many other joints are really artifacts of dissection process. Dissection can do anything you want with it. It really
Mm.
can. You can make
Anatomy
anything you
is
want with
dependent on the
dissection.
anatomist.
Um, absolutely, absolutely.
Mm.
And there are there are a few true ligaments connect bone to bone, and the cruciate ligaments is the best example. That's a true ligament, but all the others are artifacts. Van der Waal describes them as dynaments because they're actually dynamically transferring force from the muscle to the bone through what used to be called ligaments, essentially through the fascial system, whatever we call it. The term dynament hasn't really caught on. I think that's a bit unfair. I think it should. Well, in the future, I will promote it more in the future. So that's the fascia. I don't know if you want to move on to tensegrity,
No,
biotensegrity, or
absolutely, because that's obviously something now that you've mentioned a couple of times now. So to begin with, can you actually explain what tensegrity is, and then to expand on that, the concept of biotensegrity and its relationship or model for the human body?
yes, give me 10 seconds to get a model. I didn't think this was going to be on camera, so 10 seconds and I'll
Okay,
get a
of
model.
course. Yes, no, not a problem.
Right, here we go. Tensegrity, that picture I saw in a magazine 20 odd years ago, whatever it was,
Mm.
essentially was one of these. This is a tensegrity model. I don't know how familiar you are with it. But anyway, this is a tensegrity model. It's
No,
got
and I was
six
just gonna,
struts,
I was just gonna say, Graham,
yellow
because
and green struts.
I was going to say, Graham, because there may be some people who listen to this, so it's probably worth also explaining the tensegrity model of this concept of struts and elements.
Yeah, okay. The
Mm.
tensegrity model, the word tensegrity comes from the tension integrity. And it was recognised in 1948 by Buckminster Fuller, the chap with the geodesic domes, and the artist Kenneth Snelson. We recognise that tensegrity structure consists of compression struts and tension cables. And they can be arranged and put in arrangement so the struts appear to be suspended within the cable tension network of cables. And it started to get interest in buildings, have it, robotics. Space research is very interested in these structures because they're very light in weight. You can put a payload in the middle, take it up in a rocket, all folded up, chuck it out the rocket, and it unfolds, it then stands to the ground, then bounces along the ground. So robotics and space research really interested in it. Now, from a biotensegrity perspective, we have to go right down to the middle, beginning, to atoms. Think of atoms. Atoms interact with each other in many different ways. So, like van der Waals forces, covalency, hydrogen bonding, steric repulsion, many different ways, all of which can be categorized into those forces that pull atoms together and other forces that keep their centers apart, attraction and repulsion. And attraction and repulsion between atoms leads to other structures like crystals and flexible molecules, where the
Mm.
atoms interact with each other to form the crystals and the flexible molecules. And they do this through three basic principles. Geodesic geometry, because those forces of attraction and repulsion always act in straight lines. Close packing, because atoms will always try and get as close as they can to each other. And principle of minimal energy, second law of thermodynamics. And tensegrity structures are just the same. They're geodesic because cables and struts are always in straight lines, or they are in this model. We can discuss more complicated ones later. They're close packed because all the different parts get as close as they can to each other, and they always settle into a minimal state of energy. So I can push it together. The whole structure is contracting around a central point and opening out again. Tensegrity model is useful to thinking about the body. So we can think about the bones as compression elements and muscles as tension cables. Yeah, that's all right, but it's far more complicated than that. I'm jumping around a lot here. Inside cells, it's been well appreciated that the cell contains a skeleton inside it arranged like this. So it has tensioned actin microfilaments and compressed microtubules, which form this skeleton inside the cell. And a cell interacts with the extracellular matrix around it. There's a reciprocal relationship between them. So as the cell pulls on the extracellular matrix, remember, extracellular matrix is just fascia at the microscopic scale. The two are seamless, they run into each other.
Mm.
As the cell affects the extracellular matrix, so tension from the extracellular matrix influences the cell and causes it to switch between different functional states.
Mm.
Every part of the body is related to every other part. And the tensegrity system, and this is a very, very brief summary. Let's see. So I've already described the model of the cranial vault with a tensegrity structure. Use the same principle.
Mm.
The elbow is a tensegrity, where, well, if the bones are separated, which is obviously a lever system, isn't it? Must be. I mean, the textbooks say it is. Well, it looks like a lever system. But if we get down to the nitty gritty, we find that the humerus and the radius bone don't make direct contact with each other. The humerus is a bit of space between them. It's not because of cartilage. Any surgeon will tell you, if you look inside, the bones aren't jammed together like that, which is necessary for a lever system. They're just floating next to each other. They may be touching, but they're easily pulled apart in normal bones. Now, if you get into arthritic bones, yes, you'll get heavy compression there. The bones grind against each other, which leads to all the pathologies that, if you ever get the fortune to, I say fortune, to see a cadaver with a very arthritic knee, have a look at it, because it'd tell you so much the difference between a normal joint and a pathological joint. So think of the muscles of the elbow, brachioradialis, which is thought to be a flexor joint. It's only active in rapid and forced flexion and extension.
Mm.
And rather bizarrely, it's supplied by the radial nerve, the nerve that innervates all the other flexor muscles of the elbow, the biceps and brachialis. There's also anconeus muscle, which is down here, an extensor muscle, is always active before the much larger triceps. So it could be that when brachioradialis and anconeus contract, they exert a distraction force across the joint surfaces. Oh, I can't get my, across the joint surfaces that keeps the bones slight spacing in between them. There's no levers, no stress concentrations. And the biotensegrity system explains so much more. I'm just giving a brief summary of it.
But well, just to actually,
Let's see. Let me think.
just to intervene for a moment, then, Graham. So, just to make sure that I have a good understanding of this too, when we think about the concept of tensegrity or biotensegrity, we can apply this model from the cellular level all the way to the macro level. Is that correct? Because this is helping to explain the
From the
from a molecular all the way to a whole body system a model. Correct?
Yes, from the
Yes.
molecular level upwards, everything.
And
It's all
so,
part of this, where
uh,
everything is changing all the time.
yes, okay. So this helps to explain that when we think about from a movement perspective and we create movement in one part of the body, you're getting a change in force tension through that whole kinetic chain or region of the body. And it's not just the simplistic idea that if I bend my elbow, I'm creating tension purely through the front of the elbow, but there's actually forces distributed much more in a much more complex fashion. And we can even explain this from an anatomical relationship because we see that
Yes,
forces through the fascial network may be transmitted through to the antagonist and may be transmitted longitudinally through myofascial planes, both distally and proximally.
all right, you cut out there.
Oh,
But I think
it's
you were
going,
just
Graham.
paraphrasing or summarising what I'd said, I guess.
Yes, exactly. Can you elaborate,
Yes, the
Graham?
examples I give on the skull, the elbow.
Oh, sorry, Graham. There's a bit of a lag here. I'll finish and then I'll let you continue. Can you explain then a little bit more? Because you've mentioned how in this biotensegrity model, bones are essentially floating within this tensional network. So this very much challenges the concept at the moment that we have that we create stabilization through compressive forces. So that is, through gravity creating compression of bones that the muscular system sits on. And in fact, it almost
That's
reverses
right.
that concept where in the fascial network, we have muscles that provide tension to the fascial network and then bones that essentially create space to provide form of the body. Is that correct?
Yes, yes, yes. That's right. Yeah, that's right. The whole body is by tensegrity of tension and compression, and those tension and compression is changing all the time as we
Mm,
move, as we do everything we do. So the models, the skull and elbow, are just simplified models. Don't take that as biotensegrity. It's an example to illustrate a particular point. But what you said about the fascial system, tension throughout the body, and of course those compartments in it are compressed.
mm,
Bones are compressed. Muscles are compressed by the fascia surrounding them. Um, so biotensegrity, of which there's loads more, essentially it represents a paradigm shift in how we think about the human body that's not based on a lever system, not based on the idea of the body as a machine. And you may want to know, how is this useful then? I learned all this stuff. Very nice, great stuff. How is it useful to practice?
mm,
That's a thorny question that's always baffled me. No, I won't say baffled, puzzled me, because I want to give a nice answer and I can't give a nice do this and do that and hey presto.
mm,
What it is, a different way of thinking about how the body works, and not just the human body, the whole of biology operates. The concept says through a biotensegrity system, through tensegrity, balance of tension and compression, operating at every size scale. So obviously some people are going to dismiss it altogether. Fair enough. Some people, a few people have gently challenged it with me. Um, they're firm biomechanics with their levers. Um, they're not going to change. I have no intention of changing anybody's mind or what they think. I don't do this to give people great revelations. I do this because I want to know how the body works. That is my only motivation. I want to understand how the body really works. And in doing so, biotensegrity is unfolding out of it.
mm,
Um, and I want to let other people know about it, because if you think about the body in this way, through a biotensegrity perspective, inevitably we're going to think about what we do differently. What trouble is, we're all ingrained with the machine model and levers. We were taught that at school sometimes decades ago. So it's in us. We can't help but think muscles and bones and levers. But gradually explore more, you get a different feel. So you're working with somebody and you think, ooh, I wonder. I don't know. Maybe it won't happen for you.
Mm.
But that's what I just hope for everybody.
Well, the thing I think of, Graham,
There's
there's
ultimately there's
oh, sorry, I'll just ask make a point, Graham, because the thing I think about with understanding
mm,
this is there's probably two big things that stand out to me. One is that we have very much neglected the fascial system in musculoskeletal models. And clearly that has a big implication for understanding
yeah,
force creation and force transmission. Because the simplistic idea of muscles being the only element that can create force and transmit it from the muscle to the tendon to the bone clearly has a lot of limitations to understanding human movement. And I even think about that from the simple standpoint of looking at, say, muscle mechanics. And I think about, some of the really interesting work. I don't know if you've read any work from, I can't think of his first name, but Roberts, of looking at the very dynamic way that muscles can change their
mm,
architecture when you think about their fascicle length and pronation angle based on the force and velocity characteristics of the movement. And the way that it can actually alter the shape of the muscle to alter how the muscle can contract is based on how the surrounding fascial system that it's embedded in is able to shift. The other thing I think that's really important too is when you think about, say, a complex movement such as running, we obviously have very high ground reaction forces that we experience. In fact, when you think about sprinting, the ground reaction contact is around 5 times plus your body weight. And when you think about the simple idea of thinking of muscles as the contracting unit and lever arms, it really questions how we're able to be able to tolerate such high magnitudes of forces, because the muscles simply do not have the ability to create forces of 5 times our body weight. We just simply don't have. They simply do not have that capacity. And so when you start to understand the fascial system, both from an anatomical and a biomechanical standpoint, you can start to appreciate how it is able to be able to absorb a lot of those ground reaction forces, distribute them in a very complex way through the whole myofascial network, to which Biotensegrity can help explain how that force is transmitted, and then uh, be able to then transmit that forces back into the ground to propel us forward. It also then helps you to appreciate with something like running of why do we actually move our arms? And the element for that is because we're able to create a lot of force that we can then transmit through the fascial network to be able to generate a much overall larger forces in a direction down into the ground to be able to propel us forward. Or I think of, in a reverse concept, you can think about something like throwing, where throwing is a task whereby we use the whole body to be able to transmit forces from an object in our hand. Yet so much of the ability to throw that object is dependent not just on the mechanics of how we move the arm, but actually how we move through the trunk and through the lower limbs to maximize force production that's then transmitted through the fascial network to a point that of whatever object we're trying to throw. But the other one I think of too, Graham, is what you mentioned at the very beginning of this presentation, and that is for for clinicians and manual therapists. Why is it when you work on, say, the shoulder of the body, or one part of the body, a patient experiences feeling symptoms elsewhere in the body? And there isn't necessarily a neurological relationship to explain this, which I know a lot of the say
mm,
Travell and Simon's idea of referral pain is due to the the neural segments within the spinal cord. Yet some of the referral pain patterns that patients experience, or that we all experience, cannot be explained through simply a neurological relationship. So the value I see in something like this, as much as it does challenge conventional concepts, is it helps to provide a framework for understanding some of these anomalies or things that we cannot explain through some of the very simplistic models that we currently use.
yes. With integrity, when one bit moves, the entire structure moves.
Mm,
When one bit of the body moves, everything else is affected. I mean, there's something's amplified, something is dampened.
Mm,
Everything operates together. And just think, we start off as a zygote to an embryo, a fetus, baby, into adulthood, the whole of our lives. And we remain intrinsically stable throughout the whole of that system, generally. How does it do that? A machine can't do that. And the latest development that I hope to write up this year is about
mm,
superstability. It's an algorithm that keeps everything in order. We talk about homeostasis.
mm,
Homeostasis is part of that, but homeostasis is happening in all different contexts throughout the body.
mm.
Superstability, and it's a well-recognized tensegrity principle. In mechanics and engineering, we want to put it into biology to show how superstability is the ultimate algorithm that keeps everything organized and able to do all the things we want to do. And I'll throw in one little thing. Stephen Levin recently published a paper called Bouncing Bones. It's freely available, proposing that we use gravity as an energy source. And when we walk, when we run, we're actually using gravity to help us do what we need to do, which is part of everything flows towards a state of disorder, but the body can resist that and produce an enormously complex structure that survives throughout the whole of its life.
Mm.
So biotensegrity is worth giving a shot. To learn more, you learn about it, and we're just at the beginning, I think.
No, and actually, you mentioned about Stephen's recent work about using gravity to our advantage. And that to me actually makes a lot of sense because a part of human evolution is about energy efficiency. And of course, when using, say, thinking of something like gravity and using that to our advantage, as our body is accelerated down to the ground, by using those forces effectively, we can create more tension within our fascial network that then provides stability and locomotion. So it's obviously a very simplistic idea, I'm sure, to a much more complex concept. But to me, that also makes a lot of sense to how we use things like gravity to our advantage and how that could be explained through understanding how human movement and function happens through attentional stabilization as opposed to the concept of a compressive stabilization.
Mm, mm.
Graham,
The body will always use the most efficient
oh,
way of doing anything. It always
yes,
will.
yes. What's next on the horizon for you, Graham? You've obviously written several papers around the concept of biotensegrity and how this can apply to mechanics. What are you hoping to further achieve with this line of thought, and where do you see this work going next?
Um, Superstability is a thing I want to nail.
Hmm.
Put it out in a way which is understandable, um, where the body can repair, move itself, change position, transform from one state to another, and remain completely stable. We know that's what the body does. Um, and there's lots of things. I wrote the book Biotensegrity, the Structural Basis of Life in 2018. There's lots of things that have happened since then
Mm.
that I want to explore. I won't go into them now, apart from the superstability, because a lot of them are only partly half formed. So that's the direction I'll be heading.
Okay, great.
Clean all the little bits, all the loose ends that probably go off into places of their own.
Where can people follow your work, Graham? Are you someone who are you active on social media? Are all of your papers available in any particular website or resource if people want to find out more about what you do and what you've published?
Um, my website, my website, Tensegrity in biology.co.uk. That's Tensegrity in biology.co.uk. That's got almost all my papers. You can read them there, or there's links to where they can be found. A lot of them are on a paywall, but most of them are on my website to read. You can also contact me on that. I'm happy to get emails from anybody about discuss anything really. Say it's saying whatever or
Okay.
want to know more. Go on my website and contact me through there. And I don't do social media because it's far too complicated for my little brain. So
I think that's to your advantage, Graham. Sometimes it's better to stay away from social media. Graham, thank you very much for coming on and talking about your work. I it's a it is a concept that is very complex and I think very challenging to a lot of the ideas and models that we have. But at the same time too, I see that a lot of the current models that we look at how stability, how mechanics work are often too simplistic and don't take into consideration or allow us to appreciate how the body is connected. So I would certainly recommend people read your book Biotensegrity to get a better understanding of these concepts and to really start to expand or at least challenge the model of thinking about how we look at human body and locomotion. So thank you very much, Graham.
I
Do
must
you
also
want
say,
to, of
uh,
course?
I just want to say one more thing.
Yes.
Just say one more thing. Go on to the Biotensegrity archive, biotensegrityarchive.org, or Biotensegrity Archive on YouTube. There's lots of videos there on the Biotensegrity Archive
Great.
website. Some of them are quite long. There's dozens and dozens of them. So have a look. So
Great.
thank you for hosting me. My pleasure.
No, thank you very much, Graham, for coming on. And for our listeners, please do like, subscribe, leave comments to be able to help share this work and get a bigger reach for our audience. Thank you, Graham.